Here the question is, what is the chromatic number of k m comma n? Here k m comma n is nothing but complete bipartite graph with partition. Here the first partition will be consisting of m vertices, and the second partition is consisting of n vertices. For any bipartite graph, the chromatic number is 2. Why? Because in order to explain this problem, let us take one example. K. Let us take k2 comma 3. So k2 comma 3 is nothing but in the here 2 vertices, here 3 vertices. As it is complete bipartite graph, each node of this side should be adjacent to the each node of other one side, or adjacent to every other vertex of other side. That is the definition of complete bipartite graph. So here this vertex is adjacent to all the vertices of the next other side, and same is with this node also. Same is this with vertex also. So this is a complete bipartite graph k2 comma 3. So here we have to find the chromatic number of this graph. Chromatic number is nothing but the minimum number of colors needed, which are the minimum number of colors which are assigned to the vertices, so that no two adjacent vertices should have the same color. So let us take any of these the vertices of one side are not at all adjacent among themselves. So let us take these two vertices. These two vertices are not at all adjacent. So we can assign same color, the number of same color to the vertices which are present in one side. So let us take, I assign this color 1 to all these vertices, and we should assign different color to the vertices on this side, and we can assign the same color to all the vertices present this side. Why? Because these vertices are not at all adjacent, so we can assign the same color. So for any bipartite graph, the chromatic number is 2 only. For one set of vertices we can assign one color, and for the next set we can assign the second color. So here the chromatic number is 2. So here correct option is option B. Probability of occurrence of an event A is 0.7, and the probability of non-occurrence of an event B is 0.45, and the probability that at least one of A and B not occurring is 0.6. Find the probability that at least one of A and B occurs. So here probability of occurring an event A, P of A is given as 0.7. Implies P of A bar is equal to 1 minus 0.7, that is 0.3, and probability of non-occurrence of an event B is 0.45. Means P of B bar is given as 0.45. Implies P of B is equal to 1 minus 0.45, this is 0.65, and the probability that at least one of A and B not occurring, is 0.6. At least one of A and B not occurring is nothing but at least P of A bar union B bar. This is nothing but probability of at least one of A and B not occurring. That's why this bar, and it is given as 0.6. So we know that P of A bar union B bar is equal to P of A intersection B whole bar. And it is P of A intersection B whole bar. P of A intersection B whole bar. So this is nothing but P of A intersection B whole bar. We got this as 0.6, and P of A intersection B whole bar is nothing but which implies P of A intersection B whole bar is nothing but 1 minus P of A intersection B, and it is given as 0.6. It implies P of A intersection B is equal to 0.4. So we got P of A, this is intersection, P of A intersection B. We have P of A, P of B, and P of A intersection B. Now he is asking us to find the probability of at least one of A and B occurs. That means he is asking us to find P of A union B. P of A union B is nothing but P of A plus P of B minus P of A intersection B. So P of A is given as 0.7 plus P of B. P of B is B we got as 0.65, and P of A intersection B is 0.4. So this is nothing but 1.1 it's not 1.1, 1.35 minus 0.4. Sorry, here P of B bar is 0.45. That means P of B will come as 0.55, not 0.65. It is 0.55. So this is P of B is 0.55. This is 0.7 plus 0.55, 1.25. 1.25 minus 0.4. 1. Minus 4 is nothing but 0.85. So probability of at least one of A and B occurs is 0.85. So here correct option is option B.
Consider a flag pattern of 0, 1, 1, 1, 1 in bit stuffing method of framing. If message is transferred as 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0 after stuffing, then which one of the following is the original message? Normally, in a flag pattern, that is in a bit stuffing method, we used to have a flag pattern at the starting and ending in order to know the frame boundaries. So here, accidentally in the data, if any occurrence is occurred which is equivalent to the flag pattern, that is 0, 1, 1, 1, 1, we are going to stuff a bit 0 before transferring that message. That means if there are n number of consecutive ones, after every n minus 1 consecutive ones, we have to stuff 0. And that message will be delivered after stuffing to the destination. The destination will be destuffing all the bits so that the original message will be delivered, so that there won't be any confusion of the frame delimiters regarding the occurrence of the flag pattern in the middle of the data. Suppose if you take this already given stuffed pattern 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0. This is a message that is stuffed and transferred, for example. We need to find out the original message. So anyway, the flag pattern containing 4 ones, there might be 0 after every 3 consecutive ones. If there are 3 consecutive ones means definitely 0 might be stuffed. So that this is a stuffed bit, and this is a stuffed bit, and this is also the stuffed bit. If you remove these 3 stuffed bits, you can get the original message. So that it will be 0, 1, 1, 1, 0, 1, 1, 1, 1, again 0, 0, 1, 1, 1. This is equivalent to option A. So option A is the right option for this.